Okay, we're going to talk about mapping out electron density in a given molecule or ion. As we learned in the last lesson, there are regions of a molecule or an ion that can be electron rich or electron deficient, and we started looking at Lewis bases, otherwise known as nucleophiles, and Lewis acids, otherwise known as electrophiles, and saw that the base, the nucleophile, will attack the acid, the electrophile, in a reaction. And so we're really interested in being able to tell which regions of a molecule or ion are electron rich and which are electron poor. So for example, if we look at this structure here, we have a dipole. So we have a delta plus, delta minus charge distribution, and we have some lone pairs. We have pi electrons. So we have potential nucleophilicity, so nucleophilic, and then also potentially electrophilic regions of this molecule. Here we've talked about this situation as well. We have a dipole in this direction, delta plus, delta minus. We also have lone pairs here, so we potentially have nucleophilic and electrophilic sites. And then finally here we have lone pairs, dipole in this direction, right? So we have delta minus, delta plus, delta plus. So you have some electrophilic sites and a nucleophilic site here. Same thing here, you have a nucleophilic oxygen, an electrophilic carbon. You have a potentially acidic proton. And so the reason we're interested in this is because, as you've seen, it's going to determine how the molecule behaves when it's in with another nucleophile or electrophile. And one thing that you'll notice is that all of these molecules on this screen have atoms in them besides just carbon and hydrogen. What we're going to start looking at in this chapter are what are called functional groups. And so again, here are a few more examples of molecules that have atoms other than hydrogen or carbon. We call these heteroatoms. And the heteroatoms a lot of times are in charge of either making a part of the structure nucleophilic or electrophilic. The other thing that can do that are pi electrons. So when you have just carbons and hydrogens, for example, in the alkene here, this could still be nucleophilic because of the pi electrons that are there. So pi electrons are going to become important as well. Sulfur has these lone pairs, so we have a potential nucleophilic site here, potentially an acidic proton. So when we start looking at molecules, we're going to pay attention to all of these structural features, sites of electron deficiency, electron richness, where there are acidic protons, etc. And then finally down here, same kind of thing, potentially nucleophilic, electrophilic, you have pi electrons, nucleophilic, and then a potentially acidic proton. Acidic question mark, because we don't know the exact pKa. All of the other parts of this structure are going to be essentially non-reactive in terms of chemistry, because this is all just carbon and hydrogen or carbon-carbon bonds. And so if it weren't for having these heteroatoms or having pi bonds in there, these structures would not be reactive. And that's what we're going to start looking at in the next several chapters, is what types of heteroatoms and pi electrons can we introduce, what names do we give these groups, and then how are they going to behave.